Yesterday we have started with this discussion such that we have started discussing the spin orbit interaction. So as we have seen in case of alkali elements, so like sodium, potassium, etc., the spectrum of these elements is found to be actually these are one valence electron system, and the spectrum of such elements is found to be doublet. And why these doublets? So that is called as fine structure. So line of optical spectra of alkali elements show fine structure splitting, which indicates all energy levels P, D, F, etc. Okay, these are doublet except where L is equal to 0. So orbital angular momentum quantum number L is equal to 0. Corresponding orbits only not doublet. Remaining all orbits are set, all energy levels are found to be doublet. So this is due to spin orbit interaction acting on optically active electron, or the last electron which is orbiting in this particular orbit, any of the orbit, whatever orbit for a particular nuclei, a particular atom. This optical electron decides the behavior of the spectrum of this type of element, and this interaction is called as spin orbit interaction, as we have drawn in this diagram. So this atom, in an atom, this electron is supposed to move, and it has two different types of motions. One is called as spin motion, second is called as orbital motion. And because of this spin and orbital motion, both of these motions give rise to a certain magnetic moment or magnetic field, and these magnetic fields arise and they give certain interaction, which this was studied by Pauli, Darwin, Dirac, Gordon, and lot many people. So they have used a semi-classical approach to find out the interaction energy because of this type of field interactions, which is because of the spin motion as well as the circular motion or orbital motion. And therefore the interaction energy is nothing but the change in the kinetic energy of the system due to precession. Now this is what I said yesterday. This word precession is a little bit it's not difficult, but the new for us when we discuss this type of motion of electron around an atom. So this is a field interaction. So magnetic field type of interaction is there, and for that preliminary we are going to discuss one very simple concept, that this electron is revolving around a nucleus in a particular orbit, and this is looked upon as an electrodynamics. This can be looked upon as a current, or the current that is, so this can be looked upon as a current loop. So here in this diagram I have shown electron is revolving in this anti-clockwise direction. Since it has negative charge, so electron has negative charge, therefore according to the convention of the current, electrodynamics, we show current is flowing in the clockwise direction. So electron is moving in anti-clockwise direction, current is moving in clockwise direction, because the charge of this electron is negative charge, and that's why we have shown this to be direction of the electric current. This is the direction of actual movement of the electron. So this is a closed current loop. This is looked as a closed current loop, and because of this particular rule in electrodynamics, that is called as Biot-Savart's law, this is a loop where current is flowing through this circuit, and this gives rise to a certain magnetic moment. Actually here in this case this is R bar, and here I can write this V. So R bar cross V gives me actual direction of this angular momentum. Using this right hand rule, one gets this direction of angular momentum is perpendicular to this plane of this particular electron orbit and shown in the upward direction. And since charge of the electron is negative, the magnetic moment produced by this electron of orbital motion is given by minus mu L bar. So this direction of minus mu L bar or mu L bar is opposite to this angular momentum. So this is all right from electrodynamics we are taking directly, and wherein we are discussing or we are studying the behavior of electron inside an atom as a one valence electron system. Now let's see, here we are using several different concepts including precession in this case of motion of this type of electron, while we are going to describe how much magnetic field is produced because of circular motion, because of this orbital motion, spin motion, orbital motion, and this gives rise to a field type of interaction. So here we are using mathematics, here you are using electrodynamics, here you are using the quantum mechanics, here we are using the concepts of the atomic physics, etc. All these things are to be discussed in this particular derivation. Even though, as I said, this derivation is little bit lengthy, larger one, doesn't matter, we will carry out this 1 or 2 lectures as follows. Okay, so let's try and write something about this. Now this is what spin, as already we have seen, we have discussed all these things. Now consider an electron of mass small m and charge minus e, moving with velocity v bar, in a circular orbit. That is actually, it is Bohr orbit, we can say circular orbit of radius small r bar. So we may consider now this particular motion, we may consider the motion of electron. We may consider the motion of electron as a charge circulating in a closed loop. Okay, and therefore the circulating charge, this is what from electrodynamics, gives the current. Okay, this is very simple definition. Current is given by I is equal to charge per unit time, the period t required to complete one such rotation. How much time is required for one rotation? So charge per unit time, that gives you motion of the charge per unit time, that gives you current. So I am using this definition. E upon t is the current in this circulating loop, is given by this equation. I is equal to this. Okay, where this capital T is period of revolution. So has dimension of time, period of revolution. This is period of revolution, and here we have given if v, okay, scalar v, I am not writing bar over here, is the speed of electron, we can calculate. Now give this to be equation 1. Now this is speed of electron, then we have this t is equal to, now look at here, in this case t is equal to twice pi r, this is the circumference, divided by velocity v, or v is equal to twice pi upon t, or t is equal to twice pi r is the circumference of this orbit, divide by v with velocity, one gets the time required for revolution of this. Okay, this is what I get the time required for revolution of the electron are in this particular orbit. Okay, so and one more thing we can write here, and therefore equation for I can be written as, this equation can be written as, so I can write this v in the numerator, so e into small v divide by twice pi r. Okay, call this be equation 2, not 3, this is not needed. This is by current, and according to electrodynamics, actually this is called as Biot-Savart's law. This is the law, I think you might have studied it earlier, or maybe studying in future when you are learning this electrodynamics and so on. The magnetic dipole moment of such current loop, the magnetic dipole moment of such current loop, or due to such current loop, is given by, if you remember or if you know this, it is given by mu L. Okay, orbital motion is there, therefore this mu L is equal to current in the circuit multiplied by the area or cross-sectional area of the loop I into A. Since R is the radius, area is given by pi times R square, and I, as we have obtained from this equation 2, can be written here as E into V upon twice pi multiplied by R. So rearrange this, we will get magnetic moment produced here, mu L is equal to, this gives you now E, V, pi gets cancelled, one of the R gets cancelled, you will get simply it is E into V multiplied by R upon 2. E into V multiplied by R upon 2. One more thing I can do here, I can multiply this numerator as well as denominator by M. So this can be written as E into MVR divided by twice M. I can do this, where this MVR, okay, here as I showed here, this is nothing but the angular momentum PL. This is my angular momentum PL. Okay, PL. Actually, this is a vector, but I can write its unit as shown there, and therefore I can write this relation for PL is equal to, from this mu L relation, we can write relation for mu L, not PL. Therefore, this mu L is equal to MVR is PL. So this is E upon twice M into PL. Okay. Now look at this. This is the relationship. This gives me, I can give number 3. So this is angular momentum. This is magnetic momentum or orbital angular magnetic momentum. This is magnetic field produced. This is the orbital angular momentum. This is the charge of the electron, and this is its mass twice m. Had this particle been of the charge positive, म्हणजे याचा charge जर positive असता, the direction of mu L and direction of PL would have been same, in the same direction, because everything would be positive here. Since electron has negative charge, therefore direction of mu L and direction of PL are shown to be opposite. So again look in the diagram. This diagram shows you, I have shown, this is the direction of PL, angular momentum, because of this type of circular motion of electron inside this orbit, and the magnetic moment produced in this case is shown in the opposite direction to the PL, because electron has a negative charge. So that is the reference of that particular diagram. So right here, since E is negative, the magnetic dipole moment mu L is anti-parallel or opposite, anti-parallel to PL, orbital angular momentum, okay, shown in the diagram. The quantity, as we have called here to be magnetic dipole moment, this mu L represents strength of magnetic dipole, or like a magnetic dipole. So electron revolving around a nucleus in the circular orbit is as good as, electromagnetically it is as good as a magnet which has S pole as well as N pole. So this looks like a magnet, and therefore the quantity mu L represents the strength of the magnetic field. Now remember, E and M are constant. Now as electron is moving with higher and higher velocity, its PL will be bigger and bigger, and therefore mu L will be also bigger and bigger. If it is moving slowly, mu L will be smaller. If it is moving in a very fast way, then this mu L will be bigger. So magnetic field produced by electron which is rotating in circular orbit is directly proportional to its velocity. With how very high velocity it is moving, based upon that its magnetic moment will be more, or magnetic field strength in that case will be more and more. So this relationship is, so this is nothing to, it has nothing to do with this atomic and molecular spectra. These are the concepts which we studied in electrodynamics, or we are going to study in electrodynamics, but that is required here to understand what type of fields are existing in there and so on. Okay, therefore we have already written in CGS, okay, this same relation, the equation 2, equation 3 in CGS units can be written as. Now most of you might be knowing why this is written this way, written as mu L is equal to E upon twice m into C multiplied by PL, where the C is velocity of light. So this conversion factor in electrodynamics is one of the very important one. Whenever we convert any MKS quantity into CGS quantity, this C appears in such type of all relations. Well, it is not only here, but everywhere this relationship comes here. So in CGS unit, this mu L is expressed by this. So you can call this to be equation number 4. This is mu L, which is given by this. And whatever relations we have written, these are the scalar relations vectorially. So when I write this vectorially, I can write mu L bar is equal to minus E upon twice MC into PL bar. This is my relation number 5. Vectorially I am saying. Vectorially means we have to write their directions, and when we say, as we have already seen, direction of mu L bar and PL bar are opposite to each other, or because of this electron negative charge, this mu L and PL are opposite. Mu L bar and PL bar have opposite direction. That's why this relation number, equation number 4 can be written in this manner as shown by this, and therefore I can get this mu L bar upon PL bar. If I take this ratio, it comes to be E upon twice MC. E upon twice MC. Okay, numerically. Again, I have not taken this sign to be here negative. Numerically. And again, one thing, quantum mechanically, we have already written this relation, this PL bar or PL is equal to L is orbital angular momentum quantum number into h upon twice pi. This is called as quantum condition. This is called as quantum condition. So angular momentum is an integral multiple of h upon twice pi, where this L takes all the values. L is equal to 0, 1, 2, 3, 4, etc. Only all integers, positive integers, all positive integers. Okay, this is what PL. And using this particular concept, I can write, okay, again this relationship mu L can be written as okay, so write this to be E upon twice MC into, this is L multiplied by h upon twice pi. PL I am writing. So this relationship can be finally written as L orbital angular momentum quantum number into EH upon, this is 4 pi m into C. Write this quantity in the bracket and call this to be relationship number 6. Now look at this. Now we are familiar with this L. आता L आपल्याला माहित आहे, L is said to be have values 1, 2, 3, 4, etc. up to n minus 1. So here E is the charge, H is the Planck's constant, 4 pi is again a constant, m is the mass of the electron, that is constant, C in the bracket, that is the velocity of light, that is also found to be constant. So everything inside this bracket is constant. So this comes one of the very interesting constant, and that is called as the Bohr magneton. This is the unit of measurement of magnetism. That's what this value of mu L is. This is what I can have this relationship. This mu L is directly proportional to value of orbital angular momentum quantum number, and this proportionality constant is this, which is called as Bohr magneton. And this is, remember, this is the unit of measurement of magnetism of an atom. Now if L is equal to 0, mu L is equal to 0, so it won't have any magnetic moment there. If L is equal to 1, then mu L is equal to 1 into EH upon 4 pi mc, that is Bohr magneton, 1 Bohr magneton. If L is equal to 2, it will be having value 2 into Eh upon 4 pi mc. That is how this mu L is also quantized. This is also quantized. It cannot take in arbitrary values or in between values between 1 and 2 or 2 and 3 and like that. Either it will be 0 or 1 into Bohr magneton or 2 into Bohr magneton or 3 into Bohr magneton, etc. That's why this mu L is also quantized. This magnetic moment is also quantized. Okay, so we'll write in brief about this. The quantity Eh upon 4 pi mc. Now remember, you will come across this point again in electrodynamics in the second term. So this quantity is called as Bohr magneton. Okay, the quantity in Eh upon 4 pi mc in EMU, electromagnetic unit. Okay, so this is another way of describing the quantities in electrodynamics, that is called as electromagnetic unit. Represents the smallest constant value of mu L, orbital magnetic momentum, that is mu L, smallest constant value of mu L. So this is the magnitude of atomic and subatomic. Okay, so this is the magnitude of atomic and subatomic Okay, remember, we do not use this to measure magnetic moment of any magnet which we use in the laboratory. It is too big. But on the microscope scale and the atomic scale and molecular scale, this is an unit of measurement of magnetism. So that is the magnitude of magnitude of atomic and subatomic magnetism, subatomic magnetic moments, atomic and subatomic magnetic moments. Okay, and it is known as Bohr magneton. Okay, remember, everything here we have used is the properties of electron: charge, its mass, velocity of light, and h is the Planck's constant. So everything is constant, and this is called as Bohr magneton. If it is calculated, its value comes, so this is given by BH, Bohr magneton. Okay, BH, and its value is, if it is calculated, if I express all the numbers there, it comes to be 9.21 into 10 raised to minus 21 ergs per oersted, or STED raised to minus 1, ergs per oersted in EMU, electromagnetic units. If I express this in the MKS units, its value is different. In MKS units, the value of Bohr magneton, smallest unit of measurement of magnetism in the subatomic or atomic states, this is found to be 9.27. You can calculate this later on, into 10 raised to minus 24 joules in the bracket Weber per meter square raised to minus 1. See how these units are coming here. So in MKS unit, this is the value of the magnetic momentum, Bohr magneton, or in CGS or in EMU, electromagnetic unit system, this is the value 9.21. Okay, don't worry about this. So these are the, जसं आपण तुम्ही अँग्युलर मोमेंटम एचच्या टर्म्समध्ये मोजता, तसं मॅग्नेटिक मोमेंटम मोजण्यासाठीचं हे युनिट आहे, दॅट इज कॉल्ड एज बोर magneton, and its EMU value or CGS unit and its value and its MKS values can be calculated like this, and it is given numerically by E into H upon 4 pi mc. This is called as Bohr magneton. So maybe atom, maybe electron, maybe proton, maybe any molecule, whenever we try to measure its magnetism, strength of magnetism, we have to talk in terms of Bohr magneton. That is to be understood in this case very clearly. Okay, that is this. Now, as because of this circular motion, this much magnetic moment is produced. Now look at, whenever we go for this actual electron inside an atom, now in which orbit it is moving and what is value of L, based upon that it gives rise to a magnetic moment, that is mu L. That is what just now we have seen. Now it has its spin motion as well as it has this magnetic moment. So now there has to be certain interaction between this magnetic moment and this magnetic moment produced because by this circular motion, and this entire thing is called as spin and orbit interaction. Now our further derivation goes further as follows. Okay, write one paragraph here, small paragraph. The motion of magnetic moment. Now this is as good as a magnet, small magnet. The motion of magnetic moment of particle. Magnetic moment of particle. Magnetic moment of particle. Atom or molecule. Atom or molecule. You can take anything. Molecule. About the axis. About the axis of applied or external magnetic field. Applied magnetic field. This is again an electrodynamics part. Magnetic field, applied magnetic field is known as, this is again is known as Larmor, L-A-R-M-O-U-R, Larmor precession. Okay, this is an electrodynamics, again from the electrodynamics. Okay, this is called as Larmor precession. So motion of magnetic moment of either electron, atom, particle, whatever, and if there is certain external magnetic field is applied, whenever this type of motion is discussed, this is called as the Larmor precession. So this is what we have to understood again here. So in this case, the magnetic moment sweeps, S-W-E-P-P-S, okay, E-E-P-S, sweeps out a cone, about direction of magnetic field, external magnetic field at constant angular frequency. Okay? So for that we will draw this simple diagram, one simple diagram. What is that Larmor precession and how it is being taken? Okay, now suppose I am here we have this, I am given this is the direction of H. This is my direction of H, or external magnetic field or applied magnetic field, and here I am having this orbit. Okay, this orbit is shown to be of this nature. Orbit of the electron is shown to be little bit tilted. So this is the orbit of the electron that is moving around this. So it is, electron is moving this way. It is moving this way. So this is velocity. And remember, whenever it is moving this way, its orbital angular momentum is given by this vector, which is just now we have drawn in this earlier diagram. This is PL. And magnetic moment because of this orbital motion is shown by this mu L. Okay, and now what Larmor precession means, as this orbit is there in the external magnetic field, this orbit undergoes a precession. Means what happens, this PL bar rotates in a cone. This is called as precession. We have drawn one such diagram earlier too, and at the same time this also precesses around this H bar in a direction shown by this. So you can complete this. This is actually called as precession motion. What is Larmor precession means? Now look at this orbit. This orbit is shown one instance, एक instance दाखवला है. Now when this orbit undergoes precession, okay, undergoes precession means what? this orbit is changing its orientation. As it changes its orientation, this particular PL completes a rotation around this H bar, so that forms a cone there. At the same time, this mule also undergoes a precession about this H bar, and that also shows a cone. This concept is called as the Larmor precession. Try to understand what I am showing. म्हणजे आपल्याला काढताना ही डायग्राम जरी अशी काढली असली, इट्स नॉट दॅट गुड इन टेक्स्टबुक. You have been given a good diagram, you can check it later on. Yeah, I will provide this type of diagrams later on from the internet too. So this is called as precession of magnetic moment around the field direction. Okay, you can give a name, precession of magnetic moment around field direction. Remember, this is again a concept of, as I said earlier, this is a concept from electromagnetics or electrodynamics. So this is called as precession. And here आता आपल्याकडे जो इलेक्ट्रॉन आहे, this electron is also supposed to undergo the precession motion, Larmor precession inside an atom, and thereby because of that there is a spin orbit interaction or some change in the electron energies, and this change in energy is now responsible for the fine structure. This is how the connection is between all this precession and that the fine spectrum of the fine structure spectrum of that, all these things. Okay, so we have to just consider these things again. So half part of that will be discussed, and then if we'll take a break here. Okay, so the smart part of it, छोटा part अपन करें, and then we'll go here. Now right further, an electron as if it is possesses an intrinsic angular momentum. Sorry, an electron behaves as if it possesses an intrinsic angular momentum, h upon twice pi, and magnetic moment, okay, that is because of spin and magnetic moment. This electron moves in the electric field, okay, that is because of the charged nucleus, electric field E bar of the nucleus with velocity v bar. The moving electron, so such moving electron experiences a magnetic field given by, remember this is again a from electron, we are not yet entered into this atomic and molecular spectra, still we are discussing all the concepts from the electromagnetic. Now electromagnetically, in electromagnetism, the magnetic field experienced by such a charged particle like electron which is moving in the electric field of a charged nucleus with velocity v is given by its electric field of that nucleus into cross this v bar, its velocity, divide by c square. Okay, this is another directly relation taken from electromagnetics. This is again not part of our derivation, but we have to write it there. So write a number, give a number to this expression. Here I could have given this 6, now this is 7. This is equation 7. So this is again directly taken from electromagnetics. Try to understand. So this h bar is equal to E bar into V bar upon C square. Okay. Now for a nucleus, CLES, nucleus of charge Z is the atomic number into E, ZE, the electric field is given by E bar is equal to This is what your Coulomb's law. Ze upon r cube multiplied by r bar. Okay, this is actually z into e upon r square, but to write this vector form we have made this particular change here. So ze into r bar upon r cube. This is my equation number 8. Okay, now replace this equation in our equation number 7. So substituting, therefore H bar, magnetic field experienced by the electron inside an atom of charge Ze is given by, if I replace these numbers there, so it becomes Ze upon c square into r cube multiplied by r bar cross v bar, the bracket. Or I can make one more change here. This H bar is equal to Ze upon c. Now I am writing one more m there, m into c square into r cube multiplied by r bar cross mv. I am allowed to do this because I am at the same time multiplying it by m, mass of the electron, divided by its mass again. So that gives me something meaningful here, and whenever I go for this, out of this this particular, okay, according to Bohr quantum conditions, Bohr's quantum conditions, the orbital angular momentum, this is what orbital angular momentum r bar cross mv bar can be written as L star into h upon twice pi. L star is root of L into L plus 1. Try to understand this. We have already seen this, where this L star is equal to root of L into L plus 1. This is value of the angular momentum quantum number, and the value of the angular momentum quantum number according to quantum mechanics is given by this L into L bar, root of L into L bar plus into L, 1 is L star, okay, and this m is mass of an electron, and therefore my above equation can be written as, therefore the field experienced by this charged particle or electron in an atom is given by, if I use all these things there, this expression gives me L star plus into h upon twice pi multiplied by Ze divided by m into c square multiplied by 1 upon r cube. Give a number to this equation. Here this equation number is now 9. So this is how the magnetic field experienced by electron inside an atom using all these quantum conditions and etc. it is given by H bar is equal to L star into h upon twice pi Z into E upon m into c square into 1 upon r cube. Now I understood everything. H is Planck's constant, 2 pi is constant, Z is the charge of the nucleus, m is mass of the electron, c square is the square of the speed of the light, again 1 upon r cube, that r is the orbit of that particular electron in that particular case, and depending upon its orbital angular quantum number L star can be given by root of L into L plus 1. Therefore the magnetic field experienced by charged particle or electron inside an atom is given by quantum mechanically, it is given by H bar is equal to L star into h upon twice pi into Ze upon mc square into 1 upon r cube. So try to understand how this equation number 9 has been obtained and what it actually gives to us. Okay, so today we will stop here. In the next part we will go actually to this Larmor precession, how to go for its frequency of the precession, what is that actual concept. Based upon these concepts we are going to calculate what is the interaction energy of such type of Larmor precession. Remember, as I said earlier, this entire derivation is actually, it should not be in the TYBSc class because lot many advanced concepts are involved there which you have not studied earlier. म्हणजे याच्यापूर्वी बरेचसे कन्सेप्ट हे लार्मर प्रिसिशन म्हणजे काय किंवा ती इंटरॅक्शन कशी असते, क्वांटम मेकॅनिक्स कंडिशन्स काय असतात, ह्या गोष्टी आपण शिकलेल्या नाहीत. डझंट मॅटर, वी आर युजिंग ऑल दीज थिंग्स हिअर टू अंडरस्टँड Because of such type of spin and orbit interaction, the electron energy levels gets little bit shifted, and this shifts gives rise to a such type of the fine structure which we observe in doublet or triplet or whatever in case of this spectrum. So how orbits are there, how these interactions are there, how orbits are changed, how Y spectrum is changed, all these things are to be discussed one by one in this case. Okay, so in tomorrow's discussion we will go for the remaining part of this derivation. It is big one, it will require a lot of time. In examination no one asks you this, but we must understand what is this spin orbit type of interaction which gives rise to a fine structure in several different types of elements. To understand this concept, we are going for this entire derivation. Okay, so thank you. We'll stop here. Tomorrow we'll go for the remaining part of this.